Extraordinary film of extraordinary organisms in impossible places or impossibly small. It's the sort of film that we almost take for granted as part of the nightly output of our television sets, with never a thought for the problems you face as a natural history photographer.
Missed it.
Down in Oxfordshire, there's a group of ex-university zoologists who've given up their dreaming spires to become full-time natural history filmmakers. GERALD THOMPSON was a forester in Ghana before he joined the university. Out of his research, he made a prize-winning film about a wood wasp.
My trousers fall down.
Dr. John Paling was a zoologist whose speciality was a creature that lived on fishes, a louse called Argulus. Sean Morris came straight into the group after finishing his first degree. It was primarily a case of switching his attention from rowing to filming. He'd rowed twice victoriously for Oxford. Like Sean and John, Peter Parks came from the university zoology department. He's the wizard at designing intricate pieces of filming gear that Ian Moore actually makes in the workshop. Perhaps their standard lunchtime occupation is a little eccentrically effervescent, but it's a relief from their normal occupations.
Oh, very good. Brilliant.
The last member of the group, David, is GERALD THOMPSON's son. The long-tailed tit that he hopes to photograph is a fairly ordinary sort of problem. You simply move in closer over several days and take care about things like wearing the same jacket so the birds get used to it. Then you just need patience. Extreme patience. There is a more conventional way of getting near to a specific piece of behavior. If you want a blue tit like that carrying food into its nest box, then you build a hide. You can either build it slowly, bit by bit, or move it in from a distance. That gives you a fairly conventional shot. But the object of this particular group is not the conventional shot, it's the one that seems really impossible. The piece of hidden behavior, or the viewpoint that nobody else has achieved. In this case, it was Sean's problem.
But in fact, we wanted to get inside the nest and look from the other side, the side you don't normally see. And this, in fact, involved us in quite a bit of hard thinking and cunning design.
Bird again. Yes, it's female, definitely. Yes, and she's coming in, now.
Well, the setup is apparently really quite straightforward. What we've done is to mount the nest box against a blanked-off window and put a sheet of glass against the back, so they do have a physical back to the nest box, although it's transparent. You have to take quite a few precautions, I mean, apart from just setting it up as I've described, because otherwise the birds will see you behind the nest box, and any movement you make they'll detect, and this will frighten them. So we have in fact had to build another hide inside the room that this is a window to, so that I'm in a completely light-proof container in a sort of black box, peering out. My only vision to the outside world is through the blue tit's own nest hole. And the only light which actually strikes me comes from them.
So we're filming from a sort of curtained-off confessional inside the studios. It's a way of really observing a private life. For example, this is how the mother removes a sack of feces. In fact, every corner of the studio is alive. In one, there's a tea chest full of scarab beetles that GERALD brought back from France for a film about Fabre, the 19th century zoologist. And what looks like a bunch of flowers turns out to be a home for privet hawkmoth caterpillars. As far as species goes, it's a wild mouse, but after months of taming, it's become a camera hog. A menagerie of animals like this takes a fair amount of looking after. For example, Edgar the ferret must have his daily walk. That's one of Ian's jobs. And David may be working out a costing, but he's ever conscious of the needs of young Albert the owl. When we started making this film, Albert was a tiny 6-week-old fledgling who had to be hand-fed 6 times a day on minced liver with cat fur as roughage.
Look this way. Come on. That's better.
Nearly a year and a half later, he's a full-grown owl with thoroughly dangerous talons and bad-tempered with it. While we were filming him, David insisted that our cameraman must not come into the room, but just poke his lens through a protective screen.
Albert. Albert. You shouldn't be here. Come on. On you go.
He's not just a rather odd, quirky pet. One day, they hope, he'll be a very valuable artist in a future film.
Try this again. No?
The main problem with Albert is to tame him, but other creatures produce other difficulties. A bat is hard to keep still long enough to film. The trick is simple, a couple of hours of cooling in the kitchen fridge.
The ears are out, which is a good sign. He's waking up from what to him is his hibernation. And the movements of the body are really a way of getting the blood circulating again so that it's ready for flight. My purpose here is simply to get some nice side view shots of the face of the animal to cut into a sequence which will finally come as an educational film. I prepare myself to film him when his head comes round to a nice profile. In this game one has to wait days sometimes for shots, and with an animal like this you just have to be patient and wait till it does the sort of thing you're hoping for to complete a cine sequence. That's getting a bit better. Here we go. Well, that wasn't a very long shot, was it? Now it's free in the room somewhere. Now I'll get my net and see if I can pick it up. No, he's just not accustomed to all these strangers in his room blocking his usual clear spaces. Here he comes. Because their echolocation mechanism doesn't pick up this thin net, they just fly straight into the end of it. It doesn't harm them in any way, it doesn't even hurt them. Here he is. It's a beautiful little animal. This is a long-eared bat. It's one of the rarest of the British bats, and certainly one of the most attractive. This one has become almost a pet now, and is very used to handling. But with any bat, the real way of handling them for safety is to give them a half Nelson. Put your thumb down the middle of their back and pull the 2 wings back against your thumb and your other finger. And in that way the bat can't turn around and have a nip at you. The back legs, of course, have these beautiful hooked claws, and he can hang on to anything.
But now the effect of his initial cooling has worn off, and he no longer obliges by staying still.
Where's he gone now?
With insects, they carry this cooling as a temporary anesthetic even further by using a genuine anesthetic. As the cockroach comes round, Gerald hopes to get the really big close-up he needs.
They don't like sitting still, so we have to give them a whiff of carbon dioxide, which knocks them out cold. Doesn't harm them at all, provided one doesn't give them too much. They come round reasonably quickly. One usually has about a minute to a minute and a half in which one can arrange the picture and be ready for them. But obviously, until they look alert again, you can't run the camera. Come on, raise your head. Raise your head, mate. Stay put. Now he's off.
That sort of technique is fairly well established, but in this sort of filming, if you really want the unusual shot, you're constantly being faced with problems for which there is no tried answer. How, for example, if you want to film what goes on in a developing hen's egg, do you get a camera and lights inside the shell? People have tried cutting out small windows before, but that gives you a rotten view and appalling lighting problems. This technique of taking the shell away completely, Peter has developed from scratch himself.
This is perhaps the most tricky stage of all, because here we've got to try and cut this soft, slightly rubbery shell membrane without doing too much damage to any blood vessels that might be lying underneath it. And then we've got to prise the two halves of the egg away from each other. After a bit, one's hand starts to shake, and then anything can happen. That's a better cut. Now I'm going to start levering. Here the tear is starting to take place. That's going quite reasonably well. Already I can see the yolk and some of the major blood vessels lying underneath. This is where you hope that nothing slips. Now I'm pressing with finger and thumb on either side, and this keeps the gap apart. And there inside is the whole thing going on. Now I've got to draw these two halves apart, and the embryo should come away from one half. Have to do it very slowly, otherwise we'll rupture too much of the blood vessels. It's coming, I can feel it. The left hand, that's fine. There's one half away. Now, getting the second half away is more tricky because I can't catch hold of the embryo. I'm going to let it fall under its own weight, and it'll slowly flow out. It's tearing itself off the inside of the shell membrane, hopefully not rupturing too much. Here it comes, and in a minute it'll probably float down. There it goes. And there we've got a complete chick embryo out.
Even now the problems aren't over. The cameraman has also to be a physiologist. The embryo will only live if it's kept within a degree of 41 degrees centigrade, and if the fluid is at precisely the right salt balance. Chicks hatch after 21 days. This one's had 18 so far and doesn't move about much. After only 5 days, it's more interesting. Then you can see the structures within the body, even its beating heart. In this world of unlikely shots, we asked the group's founding father what had been his most difficult shot ever. A wood wasp laying its eggs was the answer. To show the eggs actually emerging from its egg-laying tube was Gerald Thompson's purpose.
The problem here was that the wood wasp drills through the bark and lays its eggs under the bark, where of course they're quite invisible. After thinking of various ways of trying to obtain a shot, we decided that the best thing was to remove a piece of bark while the wood wasp was actually at work.
Nowadays, wood wasps have become very hard to find, so Gerald showed us how it was done on a pinned specimen.
And while she's drilling down, one carefully cuts round 3 sides of a square. And then we have to attempt to prise up the bark without altering its curvature. Because obviously if you curve the bark more than it is already, or less, the ovipositor, the egg-laying tube, is pinched. And the wood wasp at once decides that it's time to move elsewhere.
He's got about 8 minutes, and it took 30 attempts to do it. This kind of work obviously takes a particular and incredibly dedicated mind, plus the specialist zoological knowledge.
Now the pin, which is pushed through the bark, represents the egg-laying tube, the ovipositor.
And without disturbing the wood wasp or damaging the ovipositor, he's got to gently lift the flap of bark up.
Well, having raised the bark, we can secure it in a vertical position with a piece of plasticine. And then very gently, we must carry it over to the table in front of the camera. And we would now sit behind the camera and hope that the eggs would begin to be extruded through the ovipositor. It's a tremendous thrill, of course. I get a tremendous feeling of privilege, you know, at seeing something which no one has ever seen before. And particularly when you see something which you didn't expect to see in the first place. One goes home so excited that I probably lose half a night's sleep. This is the effect it has on me.
Another wasp, an ordinary one, has fallen into an insect-eating pitcher plant. The problem is to get the reverse of that shot from beneath the fluid with the wasp falling towards us. This was Peter's pièce de résistance. He wasn't quite sure if it was his most difficult shot, but perhaps that's because everything tends to seem simple once one's achieved it. The plant's pitcher is hollow and normally filled with fluid in which ultimately the prey is digested. The technique is to first cut away the bottom of the pitcher. Then you wax it to a glass slide, pour back the fluid, and then it's all done by mirrors.
Well, there we are then. We're all set to introduce it to the top of the pitcher. And then through the camera here, we hope to get a view coming down and falling into the liquid in the bottom of the pitcher. We should be getting a pitcher bottom eye view.
In this sort of filming, a lot of the time is spent preparing and not much actually filming. It's a film set being watered, not exactly the Hollywood version, but even so, building them so that they look natural is a great absorber of time. Ian has designed this one to film another insect-eating plant, a sundew. The particular problem here is that the movements of the sundew when it catches its insect will be so slow that to see them they have to be speeded up, which in turn means the camera must run very slowly. It's what's called in film jargon time-lapse. It's all done electronically. This is the central brain, and once it's been started, it can run for weeks unattended. How often you expose a picture, a frame, depends on how much you want to slow down movement. This shot represents about 15 minutes of real time. Although the group reckon to be master of all technologies, underwater filming is probably their forte. In their studios you can find all sorts of creatures in about 30 tanks and aquaria that are all designed to mimic very accurately the natural conditions.
Let's take this particular tank as an example of that. As you see, it's a large tank, about 9 foot long, and at first sight it looks little more than an exaggerated fish tank you might see in any large aquarium. This particular one, however, has the specialist feature that it can be made into a river. You can hear the noise of the pump first of all, and then you see the way the weeds begin to respond and then develop this very natural waving motion, which is so characteristic of a weed in a good river current. You will see that the rush of water going from left to right will make the trout think it's natural conditions and they'll come to face head upstream again. The water is pumped by a very large pump outside, and the current flows through the window, literally, over to the end of the tank and then is recycled by being pushed along underneath the main tank to the circulating pump again. With this equipment, we've had a lot of luck in being able to kid trout that they're really in the natural river conditions. One of the snags of filming in any aquarium is that one tends to get only side views of the fish. And because we're in business to get shots that are somewhat different, and frequently the telling shots, demanding more time and frequently more equipment, we find ourselves constructing things rather like this, which is a simple periscope. It doesn't look much like a periscope when you first look at it, but the principle is very simple. You make the camera point straight down into the tank, and at the bottom of it there's a mirror at right angles which can point anywhere within the tank. So that really at the end of it one has a device which gives us the facility of shooting shots of fish which would normally be impossible unless the camera was sitting in there with the fish.
In any filmmaker's life, the most nerve-wracking, crucial time is when you first look at the rushes, the rough prints that have just come back from the processing laboratories. This is the moment when you actually meet success or failure. Of course, there are the mistakes that you saw through the camera, like the hydra that drew themselves in whenever you turn the lights up. Or the rat that was meant to feed her young, but instead took them off to a darker, unfilmable corner. And there's something very odd about this shot. The wasp's back left leg is missing, and the cameraman didn't notice it either. And with time-lapse, totally unexpected things go wrong, like the frog egg that starts developing properly, but then explodes. Or a later stage, where the frog embryo insists on turning inside its egg, which, when it's speeded up, produces a most odd effect. Then there are failures of the camera, like camera slip. It's when the camera doesn't lock the film properly for each exposure. In fact, that jerky young stickleback is from a film that Horizon asked the group to make.
Right, Mark, you've got the net.
We all talked for ages about what film they should make, and eventually decided on an old subject, the private world of the stickleback.
So who's going to carry over?
They felt they could now do this better and in more detail than it's been done before, and we, Horizon, would observe how they did it.
It's slippery down the bottom here, John. Be careful.
We'll mud up this part. That can't be helped. I think inside last...
You where's I put the jar?
You lost your jar?
Where's I put it?
Well, fill it full of water so that you're ready when you get a fish.
The film was to start with everybody's cliché idea of a stickleback, the little boy with a net and a jam jar. The location, to use film jargon, is a ditch running into the Thames near Ensham in Oxfordshire.
Really hard.
Daddy, I've got a leaf.
John Paling's own children, Mark and Sean, were press-ganged into being the little boys.
Quick, a fish!
Jolly good. That's probably in the jar then. We're just going to move a little bit upstream.
Soon, a specialized piece of equipment appeared, a field version of the periscope that they use back in the studios.
Shall we? That's it, don't go in front.
The idea was to film not only the boys' view, but also the stickleback's underwater version.
See, there's one right down.
Isn't that a clever idea?
Right down. You
Saves getting your head
Sitting down
wet.
at the bottom.
You can look underwater without getting your head wet.
We could even
Right,
see that
I
through
can
the
see
camera.
1, 2, 3, 4 there, looking at themselves in the mirror.
Immediately the story starts getting complicated, for there isn't just one kind of stickle, there are two. This is a male 10-spined stickle in his full breeding colours, and a female bulging with eggs. A male of the other sort, the 3-spined, is a different shape, a different colour, a completely different beast, in fact. What's more, the female looks quite different again. If you didn't know, you could be forgiven for thinking there were 4 species rather than 2. What's more, you could also be forgiven for thinking these fish are still in the stream. They're not. They're back in the studio filming tanks. Like so many creatures, sticklebacks have their own patch that they set up in the breeding season. The territories have no physical boundaries, no fences, and the edges just depend on who is fiercest at this particular moment. With the stickle, it's the male who sets up the home when nest building time comes. To begin with, he can't make up his mind quite where to build. He moves stones in what seems to be a thoroughly muddled, random sort of way. But even this randomness has an evolutionary purpose, for ultimately it'll bring him to the ideal spot. Laboriously, mouthful by mouthful, he digs out a trench. He gets absolutely no help from the female, and perhaps that's because she needs all her energy to get enough food to develop her eggs. If he thinks the sides of his trench threaten to fall in, then he smears glue onto the sand from a gland in his belly to stick it all together. The nest itself he makes from strands of weed. He seems to use almost any bit of anything that comes to hand, and when he gets it to the nest site, he prods it into place with his nose. Then, once again, he sticks all the bits together with the glue from his kidney gland. At this stage, he sprays sand out backwards that has fallen into his creation by sucking it into his mouth and blowing it out through his gill openings. At the moment, his drives are all to finish the nest, and if a ripe female blunders by, then he gets confused and drives conflict. The problem is that one set of drives say finish the nest, while another, stimulated by her round shape, prompt him to court her. It's easy to imagine that his fishy mind is weighing the pros and cons, but the textbooks would have it that the result is automatically inevitable. He's bound to chase her off until he's completed his preliminaries. Once he's happy he's done a good job on the nest, then he fusses around generally until the right female arrives again. Now he actively tries to court her. But there's one last check that he's got to make, that the tunnel through the nest really is there. He doesn't go through the nest at all until the female is hovering about, and so, as it's his first time through, he often gets stuck. He tries to entice her down to the nest with an elaborate and formal dance of zigs and zags and spirals in a strict order. All the conditions must be just right. She must be the right shape, or he doesn't start. He must be the right colour, in his red breeding plumage, or she's not going to respond. Once he gets her to the nest, he points the way, arching his body always inwards towards her. When she's well and truly in the nest, then he titillates the base of her tail, and she responds by slowly arching it upwards. She lays not far short of 100 eggs, each about the size of a pinhead. And once she's clear, he flashes through, and as he passes, leaves his sperm to fertilize them. Now her figure is gone. She's no longer the round shape that stimulated him, and another set of drives takes over and drive her off, they say. Now, that whole elaborate conversation wasn't a conversation at all, but a series of automatic reactions. A male will attempt to drive off a very non-fishy model if it's painted red. The shape isn't important. It's the colour that releases his response. With a model female, on the other hand, the shape is all important. It's the roundness that says, lead me to your nest. And even this totally globular nothing is regarded as a sex bomb. These experiments were in fact filmed by Gerald Thompson several years ago. when he tried to repeat them for this film, he came across a strange difficulty of biological filmmaking, that what you know to always happen doesn't happen. For some reason, the 1972 Oxfordshire stickles didn't respond as the textbooks said they should.
Let me pick your brains, John. I've got a problem at the other end.
What's that?
Models and stickleback behaviour. Last time I filmed them, about 5 years ago, everything went beautifully. And now the little blighters just won't perform. They won't show aggression towards the red. They won't...
They've coloured up though, haven't they? The fish
Oh,
themselves.
they're in good condition.
Excuse me. Hello, John Bailey.
John, it's Mick Rhodes on the phone.
Oh, fine. Put him through, will you then, Liz, please?
Hello, John.
Hello, Mick. Nice to hear you. How are you?
Well, I don't know if you'll find it nice to hear me, because the material you sent up to the labs last night, well, they had a stop in the baths, and quite a lot of the material has gone for a Burton, and a lot's been damaged.
Dear me, no.
The rolls we're talking
In most
about-
filmmaking, the day's work is immediately sent off to go through the laboratory processing baths overnight. On this occasion, there'd been a breakdown, and 13 reels of film had been damaged and 2 totally destroyed.
Something like that. And so the crucial question is, what was on 21 and 22?
Excuse me, Mick. Gerald, Mick Rhodes
This
on
is
the
what
phone.
I think it is.
I don't know.
The labs have ruined it.
Right. The bath stopped, apparently. What's on those two? Can you remember?
21 and 22
Yeah.
is the male zigging, showing the white spines, leading the female to the nest.
Mick,
Serious, a whole lot's gone.
it seems that the reels that have been picked out are the entirety of Gerald's shooting of 10 Spined.
There's no more courtship. It's all in those rolls.
So, well, what about reshooting? We put 8 days into the initial contract. At this stage of the season, how long would it take?
I think if we can get it at all, we'll get it in the same time span. I think the practicalities of this will be that we'll collect the fish and bring them in, and then feed them on, say, a special diet of things like Daphnia and Tubifex. Perhaps put special lights over them to increase the daylight, I guess.
Late as it was in the season, Ian was dispatched to grub through the ponds for a new lot of 10-spined stickles. Apart from 10-spined stickles, he also wanted an adult of one of the very large water beetles, Dytiscus, for a sequence had been planned into the film where the stickle would meet a whole array of his enemies, and Dytiscus had been cast as one of these baddies.
Bit unsafe here. I felt my jar ain't falling in.
Finding their animals is quite a major task for the group. What's more, with freshwater creatures, it's becoming more and more difficult.
Scrape along these reeds.
For it's Ian's impression that the streams and ponds around Oxfordshire are becoming more and more polluted, and the animals are correspondingly scarcer. However, the big Dytiscus beetle he wanted seems to be surviving.
Yes, and there is a Dytiscus beetle. Large water beetle. Yes, there's a leech. Not particularly interested in leeches, but I'll hang on to it just in case. Maybe of use. Well, I think I've been fairly successful today. Sometimes you're lucky and you can find exactly what you're looking for in about half an hour. Other times you may go for 2 or 3 days without really getting what you want. I've got down here an adult Dytiscus water beetle.
And what's more, he'd got what he and we really wanted. His stickles, admittedly not in breeding colours, but at least present and correct. Now it was back to the studios, and for the stickle, those extra nutritious diets and artificial electric sun. In fact, it worked. This 10-spined male is in full breeding condition. There are 2 really obvious differences between him and our 3-spined friend. That instead of a red colour to stimulate the female, the 10-spined has a pair of white spines on his belly, and it's these she's responding to. The second difference is that he's built his nest up in the trees, as it were, rather than on the ground, as the 3-spined does. In every other way, their domestic system is almost exactly like a 3-spined's. It presumably means the two species have evolved from some common ancestor, but it's the differences that are now important. Even though the tail tickling looks exactly similar, the differences prevent the species interbreeding. Once the eggs are laid, the female's function is done, and it's the male who fans his fins to keep water flowing across the eggs. And in the meantime, our three-spined friend is also fanning away in precisely the same way. The purpose of this fanning is to waft water forward with his front fins, but as this tends to drive him backwards, he has to compensate and so drives forwards with his tail. Its function is to get a good flow of water and hence oxygen to the eggs he's tending. It's not only the metabolic needs of his family that he guards. All sorts of creatures have designs on his eggs. The baddies that are the results of Ian's pond grubbing. Size seems not to deter him. If his instincts say it's important, then he drives off even a bullhead twice his size. Meanwhile, back at the ranch, things are going well with the eggs he's guarding so single-mindedly. Now, after 6 days, the eggs have eyes, and the embryo fish are beginning to twitch. Watch the top right-hand one. It was a tiny twitch, but at a greater magnification, each egg becomes a sort of rather cramped goldfish bowl. This is perhaps a good moment to pause and consider the actual filming of these tiny happenings. It's the work of Peter Parks.
Now one looks into a bowl of hatching stickleback eggs and you see little stickles coming out in all directions. That's fine. But our aim and object here is to fill the screen with one baby stickleback starting, coming out and swimming free from the egg. Problem one starts off, where is the split going to occur? How and when do you know that it's going to occur? The little stickle inside the egg may be giving little bursts of energy, and any one of those bursts of energy may split it. You might sit there for 3 hours and nothing will happen. You'll go off and spend a penny or have a cup of tea, and when you come back, the egg will have hatched.
They hatch on the 9th day, and he's now just 1/8 of an inch long. Getting this sort of shot isn't just a case of a camera and a simple tripod. It needs an optical bench. It's about £5,000 worth of fine engineering, home designed and constructed by Ian and Peter. It's the only way if you want to film a tiny stickle or a water flea.
We want to be able to go in so close that we can fill the screen with one eye. Now, at that sort of magnification, one has the big problem of vibration, particularly vibration set up by a camera, such as this, with a fairly heavy motor on it. When we start the camera, the vibration can be such that the finished image on the film just comes out a blur. One way we get round this problem of vibration is to link the specimen to the camera. We make a bench of this fairly heavy material such that when the camera starts, the vibration of the camera is transmitted through to the specimen. And this in turn means that both the camera and the specimen vibrate together. Well, we'll just roll the camera and see what happens. In fact, we're fine.
Yet another problem with such transparent objects is lighting them. Stickle eggs, for example, are so transparent that conventional lighting from behind the camera would go straight through like glass. Then you'd see nothing. This is dark ground illumination from behind, but without the light source shining straight up the camera lens and so spoiling the pictures. In a dark ground setup, the camera, the object, and the light source are in line. To prevent the light going straight into the camera, you add another lens to focus the light into a cone. Then, with a black patch, you block out the middle of this lens and the camera is now in the shade, but the object is brilliantly lit.
Now, the principle here is fairly straightforward, and we can demonstrate this quite nicely by shining a beam of light onto a lens. Up near to the lens, there's a large, dark, central area to the light, and then as we come further and further away, we're getting nearer to the tip of the cone, and now we have a fully illuminated, central, very bright spot. Now, it's there that the animal would have to be placed. Now, if the illumination was going to be correct with respect to the camera, we would have to place the camera lens right back here, and the camera lens would have to sit in the middle of that black spot.
Then you'd see the object against a totally black background. Not the black of the patch on the lens, but the black of a total lack of light. Now you can film the stickel's minuscule heart beating, and even the blood flowing through the blood vessels of his yolk sac. Ultimately, that yolk sac is gone, and they must swim for their food, which is difficult because they're heavier than water. Like most fish, they have an internal air sac to give them buoyancy, but it has yet to be filled with air, and Dad, still guarding them, tries to stop them as they struggle up to the surface. From the surface, it gulped air. Its air sac is now filled and it can swim more easily, but Dad still tries to catch it and put it back in the nest. In terms of size, he's about 1.5 inches long, and the young stickles are now about 1/4 inch. They're proper little fish, but far from out of danger. This is the underwater form of a dragonfly. The poet Ogden Nash put it rather well, writing about a mythical creature called the Wendigo, whose eyes, he said, were ice and indigo. As you are lolling hammock-wise, it contemplates you stomach-wise. You loll, it contemplates. It lollops, the rest is merely gulps and gollops. Even as the young stickles get eaten, so do their parents eat. Not their own young, but mosquito larvae. You can find them in almost any still water from April to October and from the pole to the equator, hanging from the surface, breathing through their tail tubes. As the mosquito larvae hang, they waft food and water into their mouths with a mass of beating bristles. After they've fed for about 12 days, they turn into pupae. They're entirely different to look at, but they also hang from the surface. This stage of a mosquito's life cycle lasts for another week, and then the time has come to rise up and leave the watery world to the young stickles below. For our purposes, the mosquito's actions have been speeded up about 8 times. The camera's not running so slowly that it's genuine time-lapse, but just slowly enough to make life difficult for Sean, the cameraman.
This particular shot, the mosquito emerges very steadily, and everything seems to be going very well. And yet I know very well that as soon as it's drawn its legs out of the pupal case, it takes on the rate of movement of a free adult mosquito, which is a lot faster. And ideally one would then have a camera which you can simply turn up the speed rate and carry on filming it at normal speed in the same shot, so to speak. The alternative is to do one's best to follow the animal with a very slow-running camera, this little fellow emerges. In fact, I didn't see that there was another mosquito emerging right alongside it, which was a bonus. Or at the time I thought it was a disaster. I wanted to follow this mosquito and watch it go off across the surface. And here was another wretched individual who'd come and messed up my shot. But you never know when you take this sort of shot what it's going to look like, whether it's going to be acceptable. You're struggling on the borderlines of camera technique, really.
Not all the mosquitoes actually make it. Quite a number go back beneath the water to rejoin the stickles. Stickles are fairly catholic in their taste, but water fleas, Daphnia, are high on their favourite menu. Like mosquitoes, they're common creatures, but the problem with filming them is that they're only the size of a pinhead. You're well and truly in the microscope range. In fact, Peter the cameraman was lucky here and collected a bonus with the water flea's eggs.
Daphnia are peculiar inasmuch as they retain the eggs in the body for a considerable amount of time. This eventually results in young Daphnia being liberated from their egg membranes while they're still inside the parent. And this is called brooding. The Daphnia that we were filming in this case had already hatched from their eggs inside the parent. And while we were filming them, the young Daphnia was starting to be liberated from the back of the brood pouch. Our bonus in this case was that we were able to see this birth take place.
Another morsel for another stickle. But stickles, despite their defensive spines, don't get it all their own way. They themselves are regarded as food by some. In fact, the stickle's spines served him well. What happened was that they caught in the pike's mouth, which was a good thing because the stickle doesn't seem to learn very quickly. It's still all right. The stickle's spines are firmly stuck in the roof of the pike's mouth. He may be tattered, but he's still alive and kicking. Our intrepid hero lives on to fight another day. At least, that is, until he comes face to face with a full-size pike. Spines and all, this time he's gone, which perhaps has its advantages because there are other nasties about. This is the dragonfly nymph again. On this occasion, his quarry is a 10-spined stickle. For the dragonfly nymph, it's not only the young stickles, but the adults as well that are grist to his mill. The stickle is not only surrounded by enemies that eat him in a conventional way, there are also a host of parasites that work on and in him as well. This one's called glugia. It's a relative of the malarial parasite, and the stickle's got perhaps 2 weeks to live. And this stickel's bulging belly is caused by a rather nasty gutworm, a beast called Schistocephalus. The shape it gives her is sufficient to cause a male to believe she's ripe with eggs, and he courts her. Not surprisingly, she's indifferent to his zigzag dance. The parasite, a tapeworm, can get so big that it makes up half the weight of the stickle, but to survive it must not kill its host. The parasite needs the stickle to be eaten by a predator. Its life cycle is extraordinarily complex. The adult parasite breeds inside the body cavity of birds. It travels via their droppings to a shrimp. For the parasite, the huge white mass, to reach this stage, its shrimp must be eaten by a stickle. Then the parasite or parasites grow and wait. If a bird then eats the stickle, the cycle is complete. But a dragonfly nymph simply eats the parasite. A leech, perhaps, brings together both the eater and the eaten. Attached firmly by one sucker to a weed, he reaches out for passing fish, responding to their pressure waves. Sometimes the stickles, for their part, oblige by trying to eat the leech. It's a sort of catch as catch can. Usually the battle ends up as a tug of war. But it's a war that the leech hasn't lost yet, for one sucker is now attached inside the fish's mouth, and the other he fixes to the outside of the fish. Then, by letting go his first hold from inside the stickle's mouth, he can leapfrog out and clamp both ends on the outside of the stickle. Then he proceeds for a day or two to rasp him away as food. The stickle's world is obviously a more dangerous, complicated place than one might expect. What's more, in seeing it, the stickle has rather a strange problem. It exists right inside the lens of his own eye, and it is perhaps the most curious, most extraordinary convolution to the story. As he looks through the lens from the inside outwards, there are what appear to be moving shapes lodged there. They are the larval stages of another, apparently quite harmless parasitic worm with the impressive name of Diplostomylum. Almost every stickle is parasitized in this way, and the lens sometimes writhes with a heaving mass of hundreds of the beasts. With dark ground illumination on the optical bench, the individual parasites take on shape and form. To get to the stickle, they've traveled from a predatory bird to a freshwater snail, and then right through the stickle's body to their curious home. And so, through a haze of parasites, the stickle sees his world. It's the final complication to the stickle story. It's a story where the surprising complications are the end product of millions of years of evolution. And it's really only visually that the full twists and turns of it could have been told. To tell it, as you've seen it, has taken 2 years of very single-minded expertise. Perhaps seeing how they do it will make other films like it seem more real, for although the stories that are being told are often filmed in studios, they're a true reflection of what takes place in nature, all around us, all the time.